Welcome dear learners. Welcome to the course Quantum Chemistry. In this module, we are discussing quantum mechanical tunneling. The contents of this module are Schrödinger wave equation for finite potential well, solution of Schrödinger wave equation, graphical representation of wave function and probability, quantum mechanical tunneling, tunneling conditions and transmission probability. First of all, finite potential well. Potential energy barriers are never infinite in a real world, and a box with infinitely hard walls has no physical counterpart. Hence, the problems like a particle in only box with the infinite potential wall is nearly not a practical approach. However, potential wells with barriers of finite height certainly do exist in different systems or different situations. That means it is possible to evaluate the wave functions and energy levels in such a well, such a finite potential well. Description of the finite potential well problem. Consider a particle in one-dimensional box with walls of height which is finite, that is equal to V0, and edge length or wideness equal to small a. The potential energy function is V is equal to V0 for x less than 0, that is region 1, and V is equal to V0 for x greater than a, that is region 3, and in the middle region the potential energy V is equal to 0, that is in the middle region 0 less than or equal to x less than or equal to a. This about the pictorial representation of a particle in a finite potential well. The energy E of the trapped particle is less than the height V0. This is an important assumption that the energy of the particle present in this system is always less than height of the wall. That is the description about finite potential well problem. Now, according to classical mechanics, when the particle strikes on the sides of the well, it bounces off without entering into region 1 and 3. That means, if the particle is constrained inside the box, there is no chance for moving that particle outside the walls. That is the classical mechanical situation. However, in quantum mechanics, the particle also bounces back and forth, but now it has a finite probability of penetrating into regions 1 and 3, even though the energy of the particle is less than the finite barrier. This I will make it more clear. This about the box, this is region 1, this is region 3, and the particle is confined in the region 2. And the particle is moving like this towards to and fro. The particle can move and the edge length is taken as A, and the height of the wall is taken as V0, energy of the particle is taken as E. According to classical mechanics, the particle can move to and fro within this wall and there is no chance for crossing the walls. That is, classical mechanics restricts the entry of the particle into region 3 and region 1. But in quantum mechanics, there is a chance for the finite probability of penetrating the particles, penetrating the walls by the particle. That is, there is a chance for the existence of the particles in region 1 and in region 3 rather than region 2. Now, the Schrodinger wave equation for finite potential well. And we have 3 regions, namely region 1, 2 and 3. Out of which, for regions 1 and 3, the Schrodinger wave equation is dou square psi by dou x square plus 2m divided by s cross square, where s cross is equal to s by 2 pi, known as Dirac, into e minus v0 into psi x equal to 0. Or we can simply take this as d square psi by dx square minus k square psi equal to 0, where x less than 0 and x less than a, that is for region 1 and 3. And for the middle region, that is 0 less than or equal to x less than or equal to a, this is not the Schrodinger equation. This Schrodinger equation is for region 1 and 3. In this equation, k square equal to k into 2m into v0 minus e, the whole raised to 1 by 2, divided by s cross, where s cross is a constant, that is h by 2 pi, known as Dirac. Now, for region 2, that is in the middle region, where potential energy of the particle is taken as 0, we have the Schrodinger equation d square psi by dx square plus 2m e by s cross square into psi is equal to 0. Simply psi is nothing but psi x, because it depends on one and only variable. And we get this equation because in the region 2, the boundary condition is 0 less than or equal to x less than or equal to a, and the potential energy V is equal to 0. This is same as what we learned with the particle in 1D box problem. Thus, we got Schrodinger wave equations, 2 different Schrodinger wave equations for region 1 and 3 and also for region 2. That about the Schrodinger wave equations for the finite potential well. Now, we have to discuss the solutions of the Schrodinger wave equation. First of all, solution of Schrodinger wave equation for region 1 and 3. It should be noted that the Schrodinger wave equation for region 1 and 3 will be equal to d square psi by dx square plus 2m by s cross square into e minus v0 into psi is equal to 0. For this differential equation, there will be some general solutions. And the general solution depends on the region either 1 or 3. For region 1, the solution is marked as psi 1. And for region 3, the solution is marked as psi 3. It should be noted that psi 1 equal to a into e raised to kx plus b into e raised to minus kx. But for psi 3, the solutions are more or less same, but the coefficients are different. Therefore, I marked the solution as psi 3 equal to c into e raised to kx plus d into e raised to minus kx. This means that psi 3 and psi 1 appears to be in the same form, but the coefficients AB is different from the coefficients C and D. These solutions are simply real exponents. That means there is no imaginary number or complex number I. That is, the solutions are real. This about the solution of the Schrodinger wave equation for region 1 and 3. Now we can enter into more details of the solution. We have psi 1 equal to a into e raised to kx plus b into e raised to minus kx, whereas psi 3 equal to c into e raised to kx plus d into e raised to minus kx. It should be noted that both the psi 1 and psi 2 must be finite everywhere. Also have both the psi 1 and psi 3 must be finite everywhere. Also have e raised to minus kx tends to infinity as x tends to minus infinity, and e raised to minus kx tends to infinity as x tends to infinity. These conditions leads it to the fact that two constants b and c must be 0. Therefore, we get the solution psi 1 equal to a into e raised to kx and psi 3 equal to d into e raised to minus kx. This is because psi 1 and psi 3 must be finite everywhere. That leads to the final result psi 1 equal to a into e raised to kx and psi 3 equal to d into e raised to minus kx. Psi 1 is the wave function for region 1 and psi 3 is the wave function for region 3. Now, solution of Schrodinger wave equation to region 2. I already mentioned the fact that for region 2, the Schrodinger wave equation is similar to that of particle in a potential well or infinite potential well or simply particle in 1D box problem. Hence, the Schrodinger equation is d square psi by dx square plus 2me by s cross square into psi x equal to 0, which has the solution psi 2 equal to e sin 2me by s cross 2me raised to 1 by 2 by s cross x plus f cos 2me raised to 1 by 2 by s cross into x. That is, there are sine function as well as the cosine function appears in the term psi 2. Now, wave function and probability plots. The wave function and probability plots of particle in 1D box with infinite potential well are very popular and it is known by you. Now we are discussing the wave function and probability sketch of particle in 1D box with finite wells. Wave function and probability density of a particle in a finite potential well can be plotted graphically. We are going to plot such graphs. The particle has a certain probability of being found outside the well. That is, based on quantum mechanics, there is a limited probability for penetration of the walls by the particles, and hence the particle can have a very little chance to be present outside the walls. Less than x is equal to 0 and greater than x is equal to a. This clearly interpreted when we plot the curves for wave function and probability. First of all, we can plot the wave function. This is x is equal to 0, this is x is equal to a, this is region 1, the middle is region 2 and this one is region 3. This is the ground level where n is equal to 1, this is the next level, n is equal to 2, this is the next level, n is equal to 3. We are now sketching the value of psi 1, psi 2 and psi 3. Psi 1 can be plotted in level n is equal to 1. This is the plot. Here there is a possibility for psi 1 in region 1 and region 2. Then the plot of psi 2. Psi 2 can be plotted here in level 2 and this is the plot of psi 2. And for level 3, we have to plot psi 3. Psi 3 can be plotted in level 3. The graph appears like this. So, from this, it is clear that the wave function outside the finite walls, that is less than x is equal to 0 and greater than x is equal to a, that is at region 1 and 3, not equal to 0. Since wave function not equal to 0, the probability also not equal to 0. So we can sketch square of the wave function, that is probability density, and the probability density curve appears like this. This is from x is equal to 0 to x is equal to a, x is equal to 0, x is equal to a. Being n is equal to 1, that is the first level. Next level, that is nothing but n is equal to 2, and another level, that is n is equal to 3. These are the plot of the wave function, and now we have to plot the square of the wave function to get the probability. So, in the level 1, we have to plot psi 1 square. Psi 1 square appears like this. And in the level 2, we have to plot the psi 2 square, and the psi 2 square appears like this. In level 3, we have to plot the psi 3 square, and the psi 3 square appears like this. From the curves of wave function and probability, it is clear that there is probability of finding the particle outside the well. That is, in region 1 and region 3, there will also be the probability of finding the particle. This graph can be consolidated in the coming slide. That is, this is the plot of wave function. This is the sketch of the wave function. This is level 1, this is level 2, this is level 3. For region 1 and 3, for region 1 and for region 3, the wave function outside is not equal to 0, and this is region 2. The square of this wave function leads to probability, and this is the sketch of the probability. And from this, it is clear that there is a chance for penetrating the particle into region 1 and region 3. That means there is a chance for the existence of particle outside the walls mentioned in the problem. This is possible because the wall height is finite. But this kind of behavior is not observed in the case of particle in only box with the infinite potential well. Now, we are moving to another interesting concept, that is nothing but quantum mechanical tunneling. Tunneling, by definition, is the penetration of a particle into a classically forbidden region, or the passage of a particle through a potential energy barrier whose height is greater than the energy of the particle or particle's energy. This is the crossing of a particle with low energy into a region or crossing a region of high energy. This is termed as quantum mechanical tunneling. Now, we can move on to the details of the quantum mechanical tunneling with respect to particle in a finite well. Consider a particle with energy capital E that is confined in a box which has barrier, which has a finite barrier, height of V0. The potential well having height is equal to V0. Classically, or by using classical mechanics, the box will prevent these particles from escaping due to its insufficiency in kinetic energy of this particle to get over the barrier. This I explain with the help of this symbol diagram. This is region 2 that we learned in the case of the particle with the finite barrier. The height is V0, here also V0. The energy of the particle is taken as E, but it should be noted that energy of the particle is less than V0. So, classical mechanics prevents the chance for escaping of the particle with energy by jumping into the walls, jumping through the walls. It is not possible based on classical mechanics. But in quantum mechanics, there offer a chance for the tunneling. That means the particle, even though it is having lower energy, it can cross the walls to some extent That term is nothing but quantum mechanical tunneling. This is the pictorial representation of quantum mechanical tunneling. If the barrier is ultimately thin, the particle have some probability of penetrating through the barrier without sufficient energy and appear on the sides of the box. So, classical mechanics prevents the possibility of crossing this wall, but quantum mechanics suggest the possibility of crossing these walls by penetration. This means the particle here, this is the particle. Now the particle is having energy greater than V0. V0 is the height of the wall. And for this wall or inside this, energy is less than V0. Our particle can cross through this V0 region even though its energy less than V0. So, in this wall, inside this wall, the particle is having energy less than the height. So, classical mechanics restricts the penetration, but quantum mechanics permits the penetration. That means, even though the energy of the particle present here is less than the height, the particle can penetrate into other side. This kind of penetration is called tunneling. This is the pictorial representation of quantum mechanical tunneling. This box represents the region 2 of a particle in a finite potential well. The height is V0. These are region 1 and region 3. This represents region 2 for simple understanding. Now, when the particle of energy E0 less than V approaches a potential barrier, according to classical mechanics, I already mentioned, the particle must be reflected. But in quantum mechanics, the de Broglie waves, since we are dealing with the microscopic particle, they do have some wavelength according to de Broglie relation, that is lambda is equal to h by mv. For instance, if we are taking an electron, it moves like a wave, simply known as the matter wave, with a wavelength given by lambda is equal to h by mv. So, the electron wave, when it hit on the potential well with height V0, with the potential V0, there is a chance for reflection and some extent there is a chance for transmission. That means the electron wave can penetrate through the walls. Such penetration is termed as the tunneling. So, the tunneling can be explained only by quantum mechanics. However, classical mechanics prevents the possibility of tunneling, and it should be noted that the tunneling is a phenomena that is shown by microscopic particles like electron, proton, atoms, etc. Now, this means that the particle has a finite probability of penetrating the barrier or tunneling through the barrier. Thus, tunneling is a quantum mechanical phenomena. When particle is able to penetrate through the potential energy barrier, that is higher than the energy of the particle's kinetic energy. That means the kinetic energy is even less than the potential energy of the barrier. Even though that is the situation, there is a chance for penetration. There is a chance for entry into restricted area. That is quantum mechanical tunneling. Now, the tunneling can be very nicely represented by using a pictorial representation or a pictorial notation. And how classical mechanics and quantum mechanics look into the phenomenon of tunneling. This can be explained by considering a simple illustrative example of a lion and a person separated by a wall. This is the classical mechanical scenario. Here you can see the presence of the lion in one side of the wall and the person nicely looking and happily present on next side of the wall. And he believed that there is no chance for crossing this line through these walls or penetrating this wall by the line, and this person is 100% safe as per classical mechanics. Now, what is the present situation in terms of quantum mechanics? In quantum mechanics, the situation is entirely different. The line present on next side of the wall can penetrate this wall, and this person is now not safe. So, quantum mechanics permit the possibility of tunneling, but classical mechanics restricts the possibility of tunneling. Now, conditions for tunneling. The height of the barrier must be finite. This we already discussed, because in the case of particle in a potential well with infinite height, there is no chance for tunneling. But if you finite the wall height, if you limit the wall height, then there is a chance for tunneling. The height of the barrier must be finite, and the thickness of the barrier should be thin. The potential energy of the barrier exceeds the kinetic energy of the particle. This implies that the energy of the moving particle, that is the kinetic energy of the particle, is less than energy of the potential barrier, that is E less than V0. The third condition of tunneling is that the particle has wave properties, because the wave function is able to penetrate through the barrier. The particle must have a wave character. The particle must have a wave character means it should be a microscopic body, because only microscopic particles have wave-like character. This suggests that the quantum tunneling only applied to microscopic objects such as protons, electrons, and does not apply to macroscopic objects. Now, tunneling possibility or transmission possibility or transmission probability. The probability P of a particle tunneling through the potential energy barrier is derived from Schrodinger wave equation. This is a very important relation showing the tunneling probability or transmission probability. This relation is P is equal to e raised to minus 4a pi divided by s into under root 2m into V0 minus e, and various terms present here are V0 is the potential of the barrier, E represents kinetic energy of the system, small a represents the thickness of the barrier, m represents the particle that show tunneling, and h represents Planck's constant. This about transmission probability or tunneling probability. Equation is P is equal to e raised to minus 4a pi divided by h into root of 2m into V0 minus e. It should be noted that e must be less than V0. Therefore, 2m into V0 minus e. 2m into V0 minus e. This about the situation, this about the transmission probability, and we are getting the exponential term should be negative, because V0 minus e is a positive term. Since there is a negative term, the entire exponential term e raised to the quantity that appears e raised to will be negative. That means probability need not be negative, probability will never be negative, and on solving this we will get some positive values. This we can illustrate by taking some numerical problems. And the problem is an electron with a kinetic energy of 4.50 electron volt approaches a rectangular energy barrier with V0 equal to 5 electron volt and A equal to 950 picometer. Calculate the probability of tunneling of this electron through this barrier, through the barrier. We have the tunneling probability P is equal to e raised to minus 4a pi by h into under root 2m into V0 minus we have to substitute various values to get the final value. That is A is equal to 950 picometer. 950 into 10 raised to minus 12 meter is equal to A, and V0 equal to 5 and E is equal to 4.5. Therefore, V0 minus E, that is equal to 0.5 volt. 2 into M, mass of the particle, that is mass of electron, 9.1 into 10 raised to minus 31 kilogram. And A is equal to already given. H is Planck's constant, its value is equal to 6.626 into 10 raised to minus 34 joule second. On proper substitution of all this data, we will get some exponential term, and on solving that exponential value, we are getting the tunneling probability of this problem equal to 1.03 into 10 raised to minus 3. That is, tunneling probability is 10 raised to minus 3. Tunneling probability percentage equal to 10 raised to minus 3 multiplied by 100. That is, tunneling probability as percentage equal to 0.1 percentage. This means the electron mentioned under the conditions of this problem have 0.1 percentage chance to present in region 1 and region 3 of a particle in finite potential well problem. Hence, in this module, we have discussed the Schrodinger wave equation for a particle in finite potential well, and we explained the concept of quantum mechanical tunneling. That all about this module. Thank you.